Hi, everybody. I hope you enjoyed your snow day last Friday. We've rearranged the recitation schedule slightly in terms of our coverage, so you won't actually miss any of the material. We'll basically be doing last Friday's recitation tomorrow and so forth and so on. We'll be able to catch up next week because there's a holiday on Monday and there's no lecture a week from today because the Institute's following a Monday schedule next Tuesday. So once you've been at MIT for a while, you get used to virtual Mondays on Tuesdays and things like that. So last time what we talked about was a couple things. We set out a set of construction rules that we called the static discipline for how to assemble, given a combinational device building blocks. The static discipline are rules that constrain what a combinational device has to do. And then what we did was we figured out how to hook those up in big acyclic networks, being careful not to short any outputs together. And when we did so, we discovered that we could actually build very, very large systems. And we could, you could put together some of the building blocks to make your own new, larger building block, and then I could borrow your building block and use that to build my system. So this sort of tinker-toy construction principle was possible, and it was made possible through the use of this digital signaling, where what we did is we described using the standard range of voltages that went from 0 up to some power supply voltage at this end. And we divided that up into a couple different regions. So we have these 4 voltage specifications. So any voltage less than any legal device, if it wants to output a logic 0, has to output a voltage less than VOL. If it wants to output a logic 1, this is on the output side, it has to output a voltage greater than VOH. And then on the input side, we had a different specification involving VIL and VIH. Okay, so these were the range of voltages that were considered inputs. And the difference between the output, if I'm sending information to you, between what I have to output and what you accept as inputs, this is called the noise margin. And the noise margin was very important to us because it was our ability to restore slightly flaky signals as they traveled from the output of one device to the input to the next device. Our ability to restore those values back to something that didn't have the noise, that's what made digital systems allow us to have this tinker-toy principle. So when we put all that together, and in this case what I've done is showing you the voltage transfer curve. Just to remind you what that is, right? That's a plot. If I pick a series of measurements where I select a particular input voltage, so I pick different points along the x-axis, and then I measure the output voltage of, in this case, the inverter, what I'll get is a series of data points that tell me for any particular input voltage what the corresponding output voltage was. And as we take that sort of analog world and map it onto the digital world afforded by these voltage specifications, we end up with these shaded regions. And those shaded regions correspond to, think how they work, right? So any input voltage that's a legal 0, in other words, any voltage between 0, the origin, and VIL, so that's a legal low, the voltages that range of voltages that we're going to use to represent a Boolean 0. If we do that, then we expect the device to output some sort of legal output voltage, valid in to valid out. And what that would mean is that we would expect the device to produce a voltage that's less than VOL or greater than VOH, which means that any legal combinational device, the voltage transfer curve, has to go through around those 2 shaded regions, which correspond to valid in but invalid out. So we don't ever want our devices to produce an output voltage for a specific input voltage that falls in one of those shaded regions. And the fact that that middle region here between VIL and VIH on the x-axis is narrower than it is tall, that was because we had positive noise margins. Alrighty, and it's the noise margins that allow our devices to work reliably in a whole range of environments. If we have lots of gain, so what's gain? So in terms of that gain is sort of the measure, if I make a little bit of change on the input voltage, how much of a change of the output voltage do I get? And so a device that has lots of gain would have a big change in the output given only a little change on the input. How is that reflected in the graph? Graphically, how is gain represented? It's the slope of that curve. So as the slope gets steeper and steeper and steeper, the device has a big gain. In other words, if I only make a small input change here, I go from, say, at this point in the x-axis just over just a little bit to this point, you can see the out voltage changes dramatically. It goes shoo, it falls precipitously. So that device has very high gain in that region. So lots of gain means that we can basically move these two VIL and VIH closer and closer together, and that would allow us to create hopefully better and better noise margins. Yes, question?
We want the high gain, the large gain to be on the forbidden region. We want the license stability.
Well, it's important as this thing, so this transition here where the large gain is exhibited is actually, that's a region in which the device by and large is producing illegal output voltage. So it can't correspond to any legal input voltage because then the device wouldn't be a combinational device. So in some sense, just because of the way we set things up, we always expect the high gain region to be in the gap between the two pink regions. Okay, that represents an input voltage that's in the forbidden zone. In other words, we have no particular specification for the device in that area. Okay, so what would be the ideal voltage transfer curve? If you could come up and say, okay, Chris, I understand what you're saying. If I were going to draw the ideal V in versus V out curve, what would it be? Something that gave me the best possible noise margins. Yes? Right, it would look, for an inverting device, it would look like this, where this would be basically have almost infinite gain in the middle, and for a non-inverting device it would start low and go high. So we would hope to be able to build devices that look like that. We would like them to be cheap and small, and we would like to dissipate as little power as possible. Charging and discharging, the electrons off of a wire with a little bit of capacitance will have to dissipate a little bit of power, at least in the technologies that we're using. But we'd like that to be as small as possible, and I'll come back to that. And finally, we want to build devices that will allow us to build computers and watches and cell phones. And so we're going to start starting to look at how to actually wire together electronic devices to build combinational circuits. We're going to be very interested in making sure that we can implement interesting functions. So the magic, this is, my trouble with this lecture is that I just love every slide and I could talk for a whole hour about each one. The key that we're going to use to solve the problem of how to build good combinational devices is all built around this particular device. It's called a MOSFET. MOSFET, that's an acronym. It stands for Metal Oxide Semiconductor Field Effect Transistor. And we'll see each of those words will show up in the next slide or two, and you'll get a sense of why we call it a MOSFET. On this slide, there's a couple things that I want you to notice. One is that the MOSFET is a 4-terminal device. It has 4 different connections that you need to make electrically in order for this physical device to work. And so we have a gate terminal, which that's actually it's called the gate because it's the thing that will control whether current is conducted between the source and the drain. The device is physically symmetrical. In other words, the source and the drain, there's no physical distinction between them. And so we adopt the convention that we simply label which one of the sides the source and one of the sides the drain, depending on which side has the higher potential. So we always label the side with the higher potential the drain. So that's just a sort of a labeling convention. And finally, there's a 4th terminal called the bulk, which I'll say more about. The device has 2 critical dimensions. There's the width and the length. So the length goes between the source and the drain, and the width goes across the source and drain. And the way it works is that depending on what voltage I put on the gate, current is allowed to flow between the drain and the source. So think of this as a big voltage-controlled switch where current can flow from the drain to the source. And I always say it that way because the drain has the higher potential, so the current flows from the greater potential to the lesser potential. And so the current flows across the length. It goes, you know, so if this is width and this is length, current, I'm the source and you guys are the drain, the current will be going whoosh this way, okay, across the width of the device, you know, for the width of the device all the way across the length. So the electrons are flowing from you towards me. You're the drain, I'm the source, and the gate is covering this table here. So how do I make more current flow? How do I adjust the dimensions of this table to get more current to flow? Well, as the current flows across the table from you to me, right, it basically, the electrons are flowing, there's a certain resistance that it meets because of the conductivity of the material that's forming the conduction channel between the drain and the source. And if I want to get more current, I want less resistance. And the way I can get less resistance, one is I can make the table narrower so the electrons have to flow less far across this sort of not too good a conductor. Okay, or I can make the table a lot wider and get a lot more paths in parallel. Right, so the thing that I want you to take away from this, and this is sort of the key to the sort of simple design of these devices that we're going to be doing, is that the amount of current this device will, this voltage control switch will allow is proportional to W over L. And there's never any reason to have more L than necessary. So what you do is you call up the manufacturer, you say, hello, TSMC, yeah, this is Chris at MIT. What is the smallest I can make L? And then I will adjust W to get the amount of current that I want. And depending on when I call, that number gets smaller every couple of years. Right? So when I first started out, that number was several microns. Okay, the minimum dimension. Anybody know what the sort of current smallest dimension of a modern, you know, chip that, you know, you buy from Intel is? So we went from several microns, several micrometers. Micron is just a short for micrometer, 10 to the minus 6 meters. What is it now? I heard nanometers. It's not quite 1 nanometer, but is there a number? Tens of nanometers. So we're sort of in the range where the most modern chips you buy from Intel are in the 20 some odd nanometer process, and you know, next year it'll be like 18 nanometers, right? And that number has been dropping by a factor of 2 about every 18 months for the last several decades. There's a lot of people who sweat blood off in the magic labs of people who do device physics, figuring out how to make new devices every year. That number keeps falling, and that's why, you know, electronics has really, the price has dropped and the performance has increased so dramatically over the decades. Is that this fundamental parameter, this L, has been shrinking by that factor of 2 every 18 months. That's called Moore's law. Okay, so let's think a little bit about how this magic device works. So now what I've done is I've taken a cross section, okay, and you can see the source and the drain on either side. This big thing at the bottom, this sort of pinkish area, is called the bulk. So we start off with a big silicon wafer, and we fill it with impurities so that it actually is what we call a p-type semiconductor, which means that it has a majority of carriers that are holes. In other words, you can actually get currents to flow in this device. The N-type devices are very much the same. It's a different sort of impurities that basically allow, where the majority carrier is electrons. So P-type silicon has a majority carrier of holes. N-type has a majority carrier of electrons, and we basically just, use different sort of manufacturing techniques to basically embed these diffusions into the silicon wafer, and then we build a bunch of structures on top. A little layer of insulating oxide and this gate node. So initially what happens is when we put this together, see what happened there? See how some of the pink went away? If you put these P and N type devices together, initially what happens is that the mobile carriers move around. And they actually move out of it right at the junction between the P and the N, the PN junction. What happens is the mobile carriers, what's called deplete, the depletion zone, they actually move out of there. So if you were positive, if you were a hole, you'd wander across and mate up with an N. And if you were an extra electron in here, you'd move away from the N-type devices and come find a hole to become your mate for life. And what happens is you get this depletion region, which it forms a natural insulating barrier between the N and the P. So this is a so-called PN diode. Now what's going to happen is I'm going to slowly charge up the gate. I'm going to start at 0 volts and go to 1/10 of a volt and 2/10 of a volt and 3/10 of a volt. And at some point, I'm going to get a strong enough electric field across the gate that I'm actually going to change the type of the material of the bulk region here, which had been all insulating, to N-type. I'm going to suck up enough electrons that there's now enough mobile carriers right at the surface here, right below, right underneath the other plate of the capacitor. That I'm actually going to produce a little N-type region right in the gate area because of this increased electric field, and that's going to now short together the source and the drain. So what happened is initially those two guys, the source and the drain, were isolated. Those two N diffusions were isolated. But as I increased the electric field over the table, I started getting a lot of electrons underneath, okay, on the other side of that oxide of the gate terminal. And now this guy turned to an N-type, and now I'm shorting together the drain, which is you, and the source, which is me. So I now have a conducting region. So this ability to turn it on and off this conducting region based on a field, that's why it's called a field effect transistor. Now, it's all sort of complicated. If you take 6012, you can learn all about, work functions and Fermi levels and how solid-state physics works. But for us, just think of it as a voltage-controlled switch. For this type of device, if I put a big enough charge, positive charge on this gate, I will make a conducting region between the source and the drain. Okay. Now, it turns out that FETs come in two flavors. Okay. The thing I've been talking about is what we call an N-FET, or an N-channel device. That's because the inversion, I put positive voltage on the terminal and on the gate terminal, and I attract electrons, and I connect the two N regions. So as the gate voltage goes up, what I'm going to do is attract electrons, make the inversion, and the switch goes on. So that's an N-type device. High voltage on the gate makes the switch conduct. There's a symmetrical device called a P-type device, in which the channel is actually is made up of holes. Okay, I'm going to make connect two P regions by another inversion layer, and so the P-FET and the N-FET are complements of each other. And now we get to the complementary metal oxide semiconductor, CMOS, which is what every device you own is made of. Okay, and I'm going to draw my little Valentine to CMOS here in a few minutes, and we'll see why we love CMOS. But for now, think of CMOS as made up of two complementary devices. That's complement with an E, meaning the opposite of each other. And so we have N-type devices that basically turn on when the gate voltage is high, and P-type devices, which are voltage control switches, that turn on when the gate voltage is low. Everybody sort of, you can take 5 courses here and go all the way through your graduate work to learn about all the details of why these devices work. They do. This is a very, very simplified sort of explanation of how these devices work. And we're allowed to get away with this simplified explanation because we're going to use these devices according to a set of rules that allows us to think of them as voltage-controlled switches. They're actually not quite so simple. But if we use them according to these rules, they actually behave just like voltage-controlled switches. Okay, so what we're going to do is we're going to build logic gates sort of according to the following formula. We're going to have the output node of the logic gate. So here we have an output node. And then down here we have a ground node. So this is the source of 0 volts. Think of this as the 0 volt power supply. And up here we have the power supply node, which we're going to call VDD. Okay, and so this is our source of 1, whatever the power supply voltage is. And the way we're going to build our logic families is we're going to use these voltage-controlled switches to build some sort of switching network where we're only going to use P's between the power supply node and the output node. And we're only going to use N devices in the switching network, okay, between the output node and ground. And then we have, so we'll see, here's an input, an A input that's going to some gates inside of the pull-up network. So this is called a pull-up. And this switching network is called the pull-down. Why do we call them pull-up and pull-down? I mean, they're very appropriately named. So what happens is if I close enough of the voltage-controlled switches up here, what will I end up doing if I can make a conducting path between the output node and VDD, what will happen to the output node? It gets pulled up, as the voltage gets pulled up until the power supply rail. In other words, if there's a conducting path of these voltage-controlled switches that connects this node and this node together, this node will get charged up by the power supply. How about the other way? Suppose there's not a conducting path up here, but there's a conducting path down here. Okay, then what happens to the output node? It gets pulled down. So this is called the pull-down network because its job is to discharge the output node. And this is called the pull-up network because its job is to charge up the output node, to make the output voltage high. Now I'm going to start showing you how to actually use these voltage-controlled switches to build interesting logic functions here. But that's the basic plan that we're attacking. Okay, so think of these voltage-controlled switches. I'm going to show you a simple model. They're either off or they're on. And if they're on, if the voltage-controlled switch is closed, then there's a certain resistance to the channel. In other words, it's not like it's a really great wire between the output. There's like a little resistor in here. And that you're basically discharging or charging up the output node through this resistor, which means it takes a little bit of time to do it. In modern circuitry, on the order of tens of picoseconds to charge and discharge this node. Okay, and notice that the bulk terminals here for both the N device and the P device are connected to keep the diode, PN diode junction reverse biased. As sort of a detail, when you type in your circuitry, describe your circuits to our simulators, you're going to have to remember to connect all the N-channel bulk terminals to ground and all the P-channel bulk terminals to the power supply. But that's all described in the lab. Okay, so if I hook up what's the simplest sort of network I can imagine here? Where I'm going to put in one P-channel device and one N-channel device, like so. So here's my input node here. Here's my output node. Here's VDD. Here's my ground connection. So let's build that device. That device has, first of all, notice the schematic symbols. This is an NFET. And this, the same picture, except with a little bubble on the input to remind us that it's inverting. In almost all logic diagrams, those little bubbles mean invert. So this means that this switch is conducting when the voltage is high. This switch is conducting when the gate voltage is low. So how does this work? How does this device work? If I put in a low voltage on the input, so if I put in a 0 here, what happens to the output? So think it through. If I put in a low voltage here, is this switch on or off? This guy is off. How about the PFET? He's on. She's on. It's on. Okay. So what happens to the output node? It gets pulled up. In other words, there's a conducting path between the power supply voltage and it. So this guy will actually turn into a 1. Okay, so a 0 in produces a 1 out. What about if I put in a 1 here, a high voltage? I'm just going to use our sort of symbolic name for it. It's what the power supply voltage. Now what's off and on? So how about the N-channel pull down? It's on. The N-channel pull up is off, and the output node is connected how? Through the pull-down network to ground, so it will go to 0. So what I've done is, using my voltage control switches, I've made a little device that you put in a 1 or a 0, the voltage corresponding to 1 or a 0, and what happens to the output? It inverts it. This is called an inverter. Okay, and we're going to build some other logic functions in a moment using more complicated switching networks. But in general, we're going to use these switching networks to make the output charge up through the pull-up path or pull down through the pull-down path, okay, as best we can. Now, my question to you is, what happens if I put an intermediate voltage in there? Well, they're sort of, you're not quite sure. I haven't given you enough information to really figure it out. But the choices seem to be they're both off. What happens to the output node when they're both off? Well, it's not connected to either the power supply or ground. But what happens? So what does that mean? It's floating. In other words, floating is just another way of saying it's not connected to one power supply rail or the other. What would happen to, suppose I had charged it up, so it was sitting here at a 1 value, some high voltage, and then I turned off both guys. What would you expect to happen? So if it's not connected to either ground or VDD, you'd expect it to sort of sit there and float at 1. Remember, this wire here, which goes off to other places, has some amount of capacitance. So we're essentially storing some information on the output node here. And not very reliably, because there's a small amount of leakage current that happens here. This guy, when I said he was off, I was lying. There's actually a couple picoamps of current that flow, enough so that that node will eventually get discharged. Okay, but over the course of, say, tens of milliseconds, that node will maintain its value. What happens if they're both on? What can you tell me about the output? If I have both, if I have a pull-up connection and a pull-down connection at the same time, yes? Okay, so there's a couple things. One, from a logical point of view, we probably will produce some sort of voltage sort of in the middle, which is a forbidden voltage. In other words, we don't expect a logic output from this. Okay, I'm using my battery to drive this connection. I have really bad news for you. What's the really bad news? I have a short between power and ground. And I'm dissipating power like mad. And how much power depends on the resistors, the resistance of those channels, right? So the devices you own actually have billions of these FETs in them. So that means I could actually get a pretty substantial short. So as I'm designing these pull-up and pull-down networks, if I want them to behave as logic gates but never to create a short, what do I have to guarantee? Well, that they're never both on at the same time. That would be a real disaster. Okay, or if they're on at the same time, they're only on for very, very small fractions of a second, a picosecond or two. Okay, so when I design these networks, I'm going to have to design them to be complementary. In other words, if one is on, the other is off, and vice versa. So that's the whole story behind complementary logic. Here's a picture of the VTC of a CMOS inverter. You can see that it does pretty well. It's very close to the ideal, right? It has a very large gain in the middle. Okay, so we just sort of went through this, right? When I put in a low input voltage, the output voltage is high because basically the pull up is on and the pull down is off. And similarly, when I put in a high input voltage, the input voltage is at this range, the pull down is on, the N FET is on, but the P FET is off, so I get a very low output voltage. Okay, and in the middle, I get this sort of quick change. And so I'm going to do my Valentine in just a second, but let's stop here for a second. There's one other thing I want to point out. Okay, what happens when the input is 1 here? This output node will eventually discharge all the way to ground. In other words, it's connected through this voltage control switch, and it will eventually discharge all the way to the ground. At that point, are there any currents flowing in this network at all? When there was a positive voltage here, then there was a potential across this channel resistor, and so discharge happened. But when it finally gets all the way down to 0, What can you tell me about the amount of current flowing in the network? There shouldn't be any flowing because there's no potential difference across the source and the drain. There's no potential difference across the resistor, meaning there's no current flowing across the resistor. V across the resistor is 0, so I across the resistor is 0. Right? And so what this tells me is with this particular circuit configuration, modulo little, some issues with leakage current, assuming there's no leakage current, once I've discharged that output node, no more current will flow. And the reason that your watches last a whole year on a tiny little battery is because there's no static power dissipation. If nothing is changing, if no values of the signals are changing inside of the circuit, there's no power being dissipated by the circuit. So not only, okay, do I have a very high gain, okay, I have VOHs, which are very close to, in fact, almost exactly the power supply. I have VOHs, which are very close to the power supply. VOLs, the output low, which are very close to, almost identically ground. Okay, so I end up with great noise margins. Great noise margins. So here's, apropos of probably Thursday. Okay, why do we love CMOS? Okay, and this is really part of the take-home message, right? Oh, CMOS, let me count the ways. Okay, so the one thing is that it has a very high gain in the VTC, which means I get great noise margins. And what do I mean by great? I mean large. Large noise margins. Your girlfriend will expect, or boyfriend will expect something a little bit different than this, but as engineers, this is what we love. Okay, so, and then the other thing I wanted to point out is that VOL is approximately 0 volts, and VOH is approximately the power supply voltage, and that means that there is no static power dissipation. In the steady state, this no currents are flowing. Okay, that's not true of every logic family. In fact, it's not true of almost any other logic. The reason CMOS has been king for so long is these two items. Everybody understand why we send a Valentine to CMOS? Why the digital world has happened and we carry it around in our pocket is because of these characteristics. Okay, well, we talked about, this notion of pull-up and pull-down networks and creating connections where we want them, and we talked about what happens when they're both on. This red line, we want to avoid that. And this one where they're both off, we're going to talk about memories in a couple weeks, so we'll come back to that one. So here are the complements, right? So an N-channel device conducts when its input is high, the gate is high. The P-channel device conducts when its input is low, so I can put them together in an inverter. These are complementary circuits. When one conducts, the other doesn't. Okay. Here's another. So series connections of NFETs, what's the complementary circuit? Is parallel connections of PFETs. Okay. So when A and B are both high, I get a conduction between the top node and the bottom node in this series connection. Okay. When either A or B are low, I have no path from the top to the bottom in the NFETs, but I have at least one path in the top to bottom connection of the parallel circuit of PFETs. So think of all the possible combinations of A and B, low and high, and you'll discover that one of these paths conducts and the other one doesn't, and whatever the combination is. And similarly, parallel NFETs and series PFETs are complementary. And now we have the secret to how to build CMOS logic gates. Remember you used to come in and the map of Africa was pulled down over the blackboard, in math class, and you always wondered why the math teacher had a sudden fondness for Africa, and the answer is, well, her pop quiz was underneath the map, right? So pull up the map and there would be the quiz. That's what it was when I was young. Okay, so here's a pop quiz. Here's a circuit. Can you recognize the pull-down path? That's where all the NFETs are. So that's below this output node here, which is the node with the arrow. This is the output node. Can you recognize the pull-up path? It's a parallel connection of p-FETs. So we have series n-FETs and parallel p-FETs. A and B are connected to the gates of each. So this is actually a connection from B both to the gate of this guy and then up here to the gate of that guy. Let's figure out what this gate is. This, of course, is in your notes, but you know, the idea is perhaps is to think a little bit more about how to figure this out. So when A and B are both low, so first of all, how many different combinations of A and B are there? There's two inputs, so we have A and B. So I'm going to write my little functional specification, and I'm going to do it in the form of a truth table, where I'm going to list all the possible combinations of A and B, all the possible binary combinations of A and B. So when A and B are both 0, what's on and what's off? Yes? They're both on. So the p-FETs are on. What about the n-FETs? They're both off. So what connection do we have between the output node and one of the power supplies? We have a pull-up path, so we expect the output to be 1. How about when A is 0 and B is 1? Yes?
When A is 0, the p-FET on the left is on.
Right, so this guy is on.
Yeah, that guy is on. The other p-FET is off.
Right. And what about a pull-down path?
There is no pull-down.
There is no pull-down path. Right, so again we have a high... And, I'm sorry?
There should be 1.
No pull-down path, we had a pull-up path. Thank you. Same thing here, and then what happens when they're both 1? Both p-FETs are off, and the two n-FETs are now conducting, so I actually get a pull-down path. This gate has a name, okay? It's called a NAND gate, not of AND. Okay? And you can look at this and you say, oh, okay, that's pretty good. Here's an actual picture of a mask layout. The dimensions of this thing, I've just sort of done it symbolically in terms of this basic, smallest dimension, which you call lambda. And lambda in a modern process is a couple, in this case, 25 nanometers. So this gate isn't very big. On a slightly older process, I sort of go through the mechanics of figuring out how much area this is, and on a 12-inch wafer, how many of these can I build and for how much money. And you can sort of see down here when I'm all done, the cost of one of these two input NAND gates is somewhere around 100 nanocents. And that number is probably half that cost today. Okay, so you can, for $1, you can buy, hundreds of millions of devices. Right? And Intel then sells them to you for $500, but that's, that's called profit. They have to pay for a lot of things, but they clearly have a little bit of margin to work with. All right, everybody sort of see what's happening here, right? How about this device? What's the analysis you could do? Well, you just go through the truth table here, and this is something you should work through. You should be able to figure out, for each of A and B being 0 or 1, you should be able to figure out that and come up with that as the truth table. It's called a NOR gate. Let me ask you about a different logic function. How about 0, 0, 0, 1? This would be AND. This is true when both A and B are 1. Can I build a little pull-up and pull-down networks that implement that? In other words, does this recipe work? So I have a little recipe for constructing a pull-down path, constructing a pull-down path and a complementary pull-up path. What do you think? Can I build a set of pull-up and pull-downs that implement that? Well, let me run a couple ideas behind you. When the inputs are all 0, what can you tell me about the p-FETs and the n-FETs? When all the inputs are 0, are the p-FETs on or off? They're on. So if there's any sort of network that's, will make a conducting path between the output node and the power supply, the high power supply, okay, it's bound to be turned on when these guys are all 0. So in a CMOS gate that has, this sort of one pull-up network and one pull-down network, if all the inputs are 0, what do you expect the output of the CMOS gate to be? Well, it has an active pull-up, so it must be 1. So, oops, So a CMOS gate will always produce a 1 in the case that all the inputs are 0. How about when all the inputs are 1, what will a CMOS gate produce? For sort of the symmetric reason. It doesn't matter what the network you've designed is, okay? So it turns out that CMOS, so this, can you implement this in a single CMOS gate? No, you can't. There's just something about this truth table. So we can't do this for every possible truth table. We can't build a single CMOS gate for every possible truth table. We can only build it for certain types of truth tables, the ones that describe inverting logic. Logic where rising inputs lead to falling outputs. And if you think a little bit about that, as an input rises, it's turning on NFETs and turning off PFETs. And if you're turning off PFETs and turning on NFETs, the only thing that can possibly happen, if anything happens, if something changes, if we finally get a path, is that we turn off a pull-up path and turn on a pull-down path, and the gate will fall. Rising inputs lead to falling outputs. Yes?
Why can't you switch the NFETs?
Why can't I put PFETs at the bottom and NFETs at the top, and then I could do anything I wanted to? That's a great question. The reason we can't do that is that involves an explanation about how these devices work that is far too complicated for us to go into. So remember the set of rules where we only use PFETs in the pull-up and NFETs in the pull-down? That was the set of rules that allowed us to treat these things as voltage-controlled switches. If we disobey those rules, these things no longer behave like voltage-controlled switches, and they do things that actually make what you're trying to propose, which is to use the negating switches in the pull-down path, the PFETs in the pull-down path. They won't behave the way you'd like. Okay, they don't behave as voltage-controlled switches anymore. Yes, sir?
Can we just put a NAND with an inverter?
So the way we do this sort of implementation is we build a NAND gate and follow it by an inverter. Right, so it's a little bit slower. So positive logic, non-inverting logic instead of inverting logic is basically slightly slower in CMOS than. And in the next couple of things, we'll learn how to do everything with inverting logic gates, as it turns out. Okay. Alrighty, so we have a quick review, right? We had a combinational device. We have digital inputs and outputs that you know about. We have a functional specification, and we're sort of getting a glimpse that we can, for certain functional specifications, we can come up with these connections of PFETs and NFETs that allow us to build CMOS logic that implements that. Okay, and then the last thing we mentioned was a timing specification. How long does it take for this gate to work? And now what I want to do is to talk about that. So we have this notion is that when I change the input voltage, the output voltage doesn't change instantaneously. I have to charge and discharge the capacitance associated with this wire. It's small. It's on the order of tens or hundreds of attofarads. Anybody remember what atto means? What's the 10 to the minus 18th farads? You can sort of say, that's not very much, Chris. And you can say, well, that's true, but then these resistors, these currents aren't very big either. They're on the order of picoamps or maybe microamps. Okay, so we're talking about microamp currents, or nanoamp currents, microamp currents, somewhere in there. Okay, charging and discharging attofarad capacitors. Okay, but it still takes time. It's all very small, but it takes time. It can take, getting signals to go across the network and to change them out of one of the logic gates might take on the order of tens of picoseconds, and then basically transmitting the signal down the wire. You can see it takes about 50 picoseconds per millimeter. In other words, the speed of light along these conductors embedded inside these dielectrics, these insulating dielectrics, is not quite the speed of light. And you can say, oh, this all seems pretty fast to me, Chris. Picoseconds, that seems fast. And the answer is yes, except you remember your chip is actually probably 20 millimeters across these days. And you're trying to design a set of logic and transmission wires that all operate within 1,000 picoseconds. And you're sort of going, whoa, a gigahertz processor. And you can sort of say, whoa, this is starting to be a challenge. So the fundamental limitations of physics, keep things from going too fast. They're not infinitely fast. Let me say something about how we measure delays. So what we have here is here's the input waveform, and here's the output waveform. If you look very closely at their picture, you can see on the input voltage axis here, Vin, I've carefully given you some dotted lines that represent the VIL and VIH voltage levels. So they mark the, so for a while this guy is below VIL, which means he's a valid 0, but as he changes, he crosses the input low threshold, goes up and eventually crosses the input high threshold, and at this point, right at this where I have the little cursor there, where that first vertical dotted line is, we can see that that's the first moment that the input switches to a valid high. And the way we're going to measure the delay of a gate is we're going to see how long it takes for the output of that gate to become a valid output low. So valid input high to valid output low. So VIH on the input to VOL on the output. We measure that time, and we measure it for all the devices, and we come up with a specification that is guaranteed to be longer than that measurement, the so-called propagation delay measurement. How long does it take for new information to propagate in? I've changed the input from a 0 to a 1, logically. How long does it take before I get a, in this case for an inverting piece of logic, how long does it take? This is called the propagation delay of the gate. And we have a specification such that it's guaranteed to be longer than any actual device that you buy. So if I sell you a 20 picosecond propagation delay gate, okay, what I'm telling you is if you buy all my gates and you wire them up, you will find no gate that has a propagation delay, either as the output goes from 0 to 1 or from 1 to 0, longer than 20 picoseconds. You might find some that will go in 10 picoseconds. You might find some that go at 5, but you'll never find any longer than 20 picoseconds, which was my TPD. So think of that as an upper bound in how long it takes valid inputs to be reflected as valid outputs to the gate. Everybody got that? So that's a fundamental, it hides a lot of details, but the idea is I'm coming up with a number you can use to say, I'm going to make a guess about the timing of this thing. And it's these collection of details that goes into figuring out how to build a processor that has a certain cycle time. And we'll be there in 3 or 4 weeks. Okay, there's a different sort of measurement called contamination delay, okay, which is invalid in to invalid out. In other words, how long does it take between when the input first becomes invalid? For in this case, this input crosses the VIL threshold there. It went from being a valid 0 to an invalid voltage right at this point. How long does it take for the output to become invalid? So now what we're doing is sort of measuring how, if I go from valid to invalid of the input, how long does the old good value still stick around on the output? A default assumption you can make is, if I don't tell you, always assume it's 0. Assume that the instant the inputs go bad, in other words, they're no longer valid, the output is no longer valid. So, but we do provide, in our specification, the idea of being able to tell you what that number is. And we'll actually see that in a particular case in like 3 lectures from now, where we're going to actually come back and be worried about that particular number. So we have a timing specifications where we're going to provide you with 2 numbers. Okay, how long the output stays valid after the input is changed to invalid. That's called the contamination delay. So the contamination delay is a lower bound in all those measurements. You're guaranteed that it will be good for at least that long. And the propagation delay, which is after I change the input, how long is it before the new output is guaranteed to be there? Okay, and the TPD, okay, sort of gives us information of how long you have to wait. And then after that, you're all good. Okay, now if I give you the numbers, for instance, 4 and 1 nanoseconds here, you can actually use a whole circuit here, okay, of gates, and you can say, look, I can use the TPDs and the TCDs to figure out, okay, the acyclic combinational, the TPD of that combinational circuit, that collection of gates, right? Alrighty, so TPD is the longest path from an input to the output. Looking at the TPDs of each device. What is the longest path here? If I change one of A, B, or C, what's the longest time I have to wait before Y? Yes? 12, and what you did is you looked for the longest path through the circuit and you added up the TPDs along that path. Okay. If I change the TPD of that collection, you look at all possible paths between input and output, you sum the TPDs along those paths, and you pick the largest number you find. What about TCD for this device, for this combo device? What do you have to do? Well, TCD is the minimum path, so I'm going to look for the shortest possible path and sum the TCDs. And if I do that, the shortest possible path is just 2 gates, so I get a TCD of 2 nanoseconds. Okay, I'm going to stop there. In recitation, we'll cover the rest of the last couple slides in the lecture. So good luck. You're actually at a position now where you can work on Lab 1, and I encourage you to get started soon. There's plenty of help down here in the 004 lab this week. Get a good start and come by and ask us some questions. See you in recitation tomorrow and lecture on Thursday.